of a Sunday to get this thing going. So thank you for being with us again, and kudos to your presentation, which has brought back 50-odd audience, which is pretty strong for a Sunday morning who preferred to join here today. Thank you and welcome back. Welcome, Dr. Roy, welcome, Mona Lisa, and good morning and welcome one and all of this learning community for being with us today, the second day and the concluding day of this materials characterization series organized by the Department of Material Science and Technology of Maulana Abul Kalam Azad University of Technology, West Bengal. Yesterday was the first session by Dr. Rudra Samastar, and it addressed a few aspects or in the scale of the light matter interaction. It addressed, for example, the bond in the scale where the bond forms, then the molecules, and some short range order. And a couple of places were mentioned, but those were not elaborated, such as the atom and the long range order. So it's my guess that Dr. Samajdar will pick up from where he had left yesterday and share with us another illuminating session. Welcome, Dr. Samajdar.
Thank you. Thank you, Professor Samajdar. Thank you, Dr. Roy, and thank you, Dr. Char. It's wonderful to be back again. And thank you, the audience, for taking time off on your Sunday morning to join this session. I promise I won't take very long, and I'll just try to wrap up, the sort of picture that I left somewhere in between from yesterday. So quickly, if I may, I'll just share my screen and right. Sorry. So
yes,
you are able to see my screen. I'll just put this on full screen mode, if that's okay. And all right. So yeah, so you've slightly taken the liberty of tweaking my title, this being the second day. So it was lighting up matter, and I talked about absorption, emission, a little bit of scattering yesterday, if you remember Raman scattering. And so there are a couple of things that I just want to continue with today. So it's a little more light and a few more curiosities. So before I start, just a sort of quick recap on things that I discussed yesterday. The first thing that we started with was a bit of molecular dynamics, in the sense that the different ways in which molecules move, things like translation, rotation, vibration, so on and so forth. I discussed a little bit on symmetry properties, on the way that one tends to understand molecules in terms of the symmetry properties present, inherently in them. I've discussed ways of representing molecules on a computer, and how to do sort of very basic level computation so that you can visualize processes in molecules such as vibration and so forth. This was the sort of first part of the module, and we moved on from this part of the module to studying light matter interaction, something known as time-dependent perturbation theory, and sort of like the mathematical framework. I didn't discuss obviously the mathematics in detail, just sort of a basic flavor of the kind of quantitative approach involved in understanding spectroscopy. And I discussed a little bit about electronic absorption, emission spectroscopy, and vibrational spectroscopy, with a few examples of experiments that I've done on my own, and a few examples of experiments from the literature. I'd also discussed a bit about scattering, X-ray absorption, and synchrotrons. And that is where we'd left it hanging, telling that, all of these techniques help you probe bonds, molecules, and then maybe a little bit along the sort of local order around molecules. But what about things that lie on the other two extremes? That is, when you want to probe atoms, when you want to probe molecules packed together in sort of a kind of a continuum large-scale structure, such as crystals. So this is where we are going to start off today. But before I do, since I did this recap, do you have any questions on what I've discussed so far yesterday? Feel free to put this in the chat box and I'd be happy to take them up. If you don't have any questions on what I've discussed so far, I'll quickly come back to some of the questions that you had asked yesterday. So just following up on this, there was a question yesterday on the sort of general idea behind perturbation. And this is a sort of reading suggestion that I've recommend. Now, there's no need to copy this down because I'm going to share the slides with you at the end of the day. Maybe I'll just put them together in a PDF and share. But quantum chemistry by Levine has a good sort of general treatment of time-dependent perturbation theory that you can use to understand what are perturbations and what involves, putting systems out at equilibrium. And just as a sort of quick aside in this context, systems being out of equilibrium are very, very, very important. In fact, for those of you who come from a sort of physical chemistry background, you might have heard about this prominent area of work of research known as non-equilibrium thermodynamics. So one of the pioneers of non-equilibrium thermodynamics, I think he was a Belgian, Professor Ilya Prigogine, has this very sort of elegant comment telling that matter at equilibrium is essentially blind. And when you go away from equilibrium, you begin to see. So perturbation is actually a way of sort of trying to drive the system out of equilibrium. Read about it if you're interested and if you want to understand spectroscopy a little bit more in detail. There was another question on spontaneous emission. And this was, this is more sort of associated with lasing and the physics associated with lasers. Lasers, by the way, are a very, very, very important class of techniques which can be used to study ultra-fast processes in chemistry. You can read about spontaneous emission on Walter Struve's book, which is an excellent resource, and also from Peter Bernard's book. Both of them require a sort of basic sort of prerequisite understanding in mathematics, but I'm sure most of you have that from your undergrad days, so it shouldn't be a problem. Sorry, a few more things. There was a question on iron oxide and how it could be sort of distinguished by X-ray absorption. So these are two excellent sources on the internet. They're both open source, where you can actually download X-ray absorption spectra and take a look for yourself how different materials have different X-ray absorptions depending upon the local chemical environment. All you need to do is just download the file. You can download an image and take a look and see how they compare. Another thing was basically visualization of structures. Remember, I'd shown this kind of a carbon dioxide molecule and a water molecule yesterday, and I'd spoken about how to represent water, for example, using Z matrices and XYZ files. So these are two sort of common open source softwares. You can download them on your Windows machine, or if you use a Mac or a Linux system, they're open source. And once you download them, you can set up your own structure and try to have a look at the structure in 3D, sort of make it turn around, make it do a little bit of vibrations, and just have a feel for the process. And obviously, as most of you are probably aware, ChemDraw is the sort of standard source for drawing structures, but however, ChemDraw requires a license, which can be pretty expensive. This thing from Perkin-Elmer crowd is a sort of open source equivalent of ChemDraw. It comes from Perkin-Elmer, who are the manufacturers of ChemDraw, and you can use this to draw structures and then transfer them into these kind of visualization softwares to understand, the dynamics in molecules. I hope this is sort of helped those of you who had asked these questions, and apologies, I'll just now quickly move on. And this is something that I want to quickly add as a sort of addition to the absorption spectra that we had discussed yesterday. This is also sort of like sort of aside. This is also basically absorption, but with a slight kind of additional factor to it, which is called polarization. Now, as you probably are aware, light can be polarized, and polarization means effectively that the electromagnetic waves have basically electric and magnetic fields vibrating perpendicular to each other and perpendicular to the sort of direction of propagation of the light. And if you are sort of able to confine these vibrations either in a particular field or make them rotate slowly, you get linear as well as circularly polarized light. Now, usually when we talk about absorption, molecules absorb energy, and this gives rise to UV visible structures in spectroscopy, as we discussed yesterday. However, let's say you have systems which are chiral in nature. So for those of you who are from a chemistry background, you already know that chirality is sort of an inherent property in chemistry, where you have two different systems which are not superimposable mirror images of each other, right? And those are known as you're aware, they're known as enantiomers, and from there you can move on to diastereoisomers, so on and so forth. So if you have a pair of enantiomers, or if you have something which is chiral in nature, and you put in regular light, then obviously regular light is not going to be able to distinguish between your two chirally different forms. However, if you put in circularly polarized light, there'll be a differential absorption between right circularly polarized and left circularly polarized light. This is known as circular dichroism spectroscopy. It's essentially exactly same as UV visible spectroscopy. The only difference being that in UV visible spectroscopy, you're putting in regular light, regular in the sense that it's not circularly polarized. However, when you do CD spectroscopy, you put in left and right polarized light, look at the differences in absorption, and then understand chirality. These are useful for understanding biomolecules, especially, for example, structures like alpha helices and beta sheets, and local molecular environment. This is a sort of typical comparison that I've taken from this classic textbook on physical biochemistry. So here you have a UV visible spectra with, let's say, an absorption around 260 to 280 nanometers of wavelength. This area usually comes from, molecules such as tryptophan, which are present in proteins. The absorption is regular here. But the moment you put in left and right circularly polarized light, this band, as you see here, splits. So splitting of bands, as you see in CD spectroscopy, is important. It tells you that there is handedness in the structure. And this kind of a splitting of band is also known as the Cotton effect. For those of you who are from a chemistry background, again, Cotton is the same F. Albert Cotton, who's written the famous textbook on group theory and a famous textbook on chemistry. You might be referring to it in your regular courseware in undergrad and postgrad courses. Right, so this was just a quick addition to absorption from yesterday. And this is where we stand since yesterday. So, IR, Raman, spectra helps you. So sort of this is the area in which we are moving: atoms, bonds, molecules, local chemical environment, and then extended structures, which are essentially crystals. So IR for probing vibration between bonds, Raman also for probing vibrations, but with a slightly different kind of information space. UV visible spectra for understanding conjugated molecular systems, a bit of local chemical environment, a bit of bond as well. Then fluorescence, time resolved and steady state, to understand the kind of structures and local chemical environments involved around molecules. And also, especially if you're doing time resolved data, to sort of understand the kind of time scales involved. Time scales in spectroscopy are also very, very, very important. Till now, we've been only talking about length scales. We'll come back to time scales towards the end of the talk. And this gives you some idea. Fluorescence spectroscopy gives you some idea about time scales. X-ray absorption gives you some information about local molecular environments, requires access to amazing places which are known as synchrotrons. And circular dichroism also gives you some information around here. So we are left with blank areas here and here, with which we would like to sort of address. But before we start, we still have a problem from yesterday. So this was, I don't know if you have time to think about this. So there was this kind of a vibrational spectroscopy experiment that I was doing. And what it involved was taking an ATR crystal and coating a thin layer of gold on it. And just ignore this thing for the time being. It's essentially a kind of an electrochemical cell. However, what I wanted to drive in was basically that when I had this thin layer of gold on this, I was getting these kind of weird spectroscopic signatures instead of a regular kind of vibrational spectra. So the question was that what is wrong with our FTIR experiment? Now, before I give you the answer, I'm sure some of you have thought about it, but in the interest of time, maybe before opening the floor up for the answer, I'll just sort of discuss the kind of approach that I took. We'll have a question sort of in question session a little bit after this. But the sort of diagnosis for this problem was as follows. Sort of, if those of you who are a fan of this particular gentleman, House MD, it's a sort of popular show, or the popular TV show. The Dr. House is sort of known for very sort of eccentric ways of making diagnoses of diseases. However, that sort of thing aside, what happened was that, when you have regular vibrational spectra, it is sort of a synthesis from an interferogram, right? An interferogram is the sort of basic fundamental observable that you have. You do a Fourier synthesis on that, and then you sort of get a vibrational spectra. Now, if you have this kind of weird structures in the vibrational spectra, it means that there's something wrong in the Fourier synthesis, that there's something wrong in your interferogram. Now, what we noted was that there's a kind of a spike in the interferogram, and this spike is not supposed to be there if it's a regular. Why is there a spike? Now, for this, we need to go back to the kind of system that we were studying, and there's a thin layer of gold on the IR crystal. Now, for those of you, you might be aware of this. If not, there's an interesting thing that does happen, is that when you're going at nanometer, since you're all from material science background, it's good to know that when you go to low dimensions in material, low dimensions, by low dimensions, I mean nanometers and less, there are sort of weird, wacky effects in quotes that come up in the material. And there's something known as a Peierls distortion. And this happens in low dimensional materials. What is a Peierls distortion? I won't go into details. That's a lot of sort of advanced quantum mechanics. But suffice it to know that if you have a 10 nanometer layer of gold, it is not uniform. There is a distortion in this sort of lattice, and this is known as a Peierls distortion. And this distortion can give rise to sort of unusual reflections here, which sort of affect the evanescent wave. And this gives rise to kind of a weird structure in the interferogram. And voila, you have this kind of weird wavy sort of sine wave in your spectrum. This was something interesting that I found out just last week when I was doing a couple of experiments in the lab, and just wanted to share them with you, just to let you know that even regular benchtop IR spectroscopy can be really painful at some points of time if you're not sure of what's happening. Coming sort of a quick follow-up from Peierls distortion, those of you who are aware of this molecule, it's known as polyacetylene. It's important because it's basically acetylene polymerized. So you have alternate double and single bonds ideally. It is an important thing because these were sort of initial candidates for organic electronics. So now for those of you who know that, they have some very wonderful televisions and electronics today, which are based on organic materials. For example, I was just having a look at I think an advertisement by Samsung yesterday. Nowadays you have flip phones, so you can actually sort of flip the phone and fold it. And that is possible because of organic light emitting diodes displays, which are sort of soft and flexible. Right. And that's a sort of emerging and very, very, very sort of popular and resource intensive area of material science, where industry puts in a lot of investment and requires a lot of good chemistry. And maybe some of you will go into this in your careers later as in the industry or in academia. However, just the reason why I mentioned polyacetylene was that this is another molecule that shows Peierls distortion. These are one-dimensional chains, and you see alternate double and single bond kind of structures instead of a kind of Huckel resonating sort of uniform single resonating structure. And for those of you who have done a bit of physical organic chemistry, this is nicely discussed in Anslin and Doherty's text. And the molecules are intricately connected with the emerging area of organic electronics and optoelectronics, something which Professor Moitro mentioned yesterday at the end of the session. That this is an area of optoelectronics or organic electronics is a sort of very vast and important area that's developing in recent times. Right. So having done this, we can move on to the sort of the main part of the lecture today. However, before I do this, I just wanted to show you something. And that is, if I may, I'll just try to share another screen. And right. So, spectroscopy, a lot of part of spectroscopy goes in, sort of doing transformations and then finally presenting the thing that you see on the screen, right? So this is, for example, the software that I'm showing here is known as Omnic. It's essentially a software used, it's a sort of licensed software that is used for understanding vibrational spectra. So if I go to process and convert this to percentage transmittance, so this is the sort of IR spectra that you're used to seeing in your textbooks. This is wave number, this is percentage transmittance, and the molecule that you have here is tetrahydrofuran. It has some of these CH stretches here, and it has some CO stretching here. And as I mentioned yesterday, these can be used to diagnose the kind of bonds present in the molecule. So taking a look here, you can say that there are CO bonds present, there are CH stretches present. And if you're good enough, then you'll be able to predict that, okay, this is the IR spectra for the DHF molecule, even if I don't tell you what this is. Now, this is the sort of end product, right? So what does the machine give you? The machine gives you an interferogram, right? So if you want to look at the interferogram, what do? You sort of do a reverse Fourier transform. Doing this is a bit involved. You can do it in sort of common platforms such as Python, MATLAB, R, those of you who are aware of this. Now I'll take the sort of easy shortcut out and do it on this software where the thing is sort of inbuilt. So I'll go here and click on retrieve interferogram. Immediately the thing becomes very noisy because interferograms are inherently noisy, but I'll take you to the point of zero deflection and then just try to sort of do a full scale and voila, there you go. So this is not something that you'll see as the end product. The end product is your nice transmission versus wave number. But this is the kind of information that you get from the spectrometer in itself. This is a raw data of interferometry collected by the spectrometer. There's a lot of good math that goes on. Like I keep on telling, without math, you can't do spectroscopy, or essentially you can't do chemistry at all, except for some very specialized areas. And there's a lot of good math that we don't care about as spectroscopists because we are concerned with the end product that goes on in sort of synthesizing the observable spectra from this kind of raw data. Right, and so just sorry for this, but just wanted to share this with you, and I'll come back to my presentation about IR. And now that we have this, we now have, let's say, we come back to our sort of guiding map again. We have IR, Raman, CD, X-ray, visible fluorescence. We've solved a problem with the IR, sort of tried to discuss what sort of weird effects can actually complicate very simple IR spectroscopy. And I've tried to show you sort of short example of how mathematical treatments are involved in processing spectra in general. Now, I'd be happy to sort of move on to, let's say, this area of spectroscopy where you want to probe atoms. And this is what is known as nuclear magnetic resonance, NMR. Remember, I told you yesterday that when you have absorption can happen in nuclei also, and that gives rise to nuclear magnetic resonance. As a quick start, you'll probably be reading about it a little bit in your sort of self-learning program. But the first observation of nuclear magnetic resonance was done in the sort of middle half of the 20th century by two independent workers. I think Bloch was at Stanford and Purcell was in Harvard, or it was probably the other way around. And this sort of made them win the Nobel Prize in 1952. And much later in 1991, just sort of the end of the millennium, we had Richard Ernst from, I think, the University of probably Basel in Switzerland, who also won the Nobel Prize for designing sort of more complicated systems in NMR. The reason I've put this is that there are not many areas where, basically development of methods results in back-to-back Nobel Prizes or results in multiple Nobel Prizes. There's only one more technique that I know of, which has resulted in 2 Nobel Prizes and probably no prizes for guessing. That's X-ray crystallography, which we're going to talk about a little later in this lecture. So yeah, 2 Nobels. So a fascinating sort of field, basis of the MRI kind of diagnostics that are extremely crucial in medical science nowadays. A quick sort of talk through the kind of physics involved. So as the name implies, it probes nuclei, and I'll be talking about the proton because that's the simplest nuclei that you can think of. The H+ atom, it has just one proton sitting inside the nucleus, right? So there's a bit of underlying physics in it. Not a bit, there's a lot of underlying physics in it, and the physics of NMR is seriously very, very, very complicated. However, I'd just like to sort of give you a very top level view as I promised yesterday. So when you have, let's see, I'm talking about proton NMR. Proton NMR is the most common NMR that you'll find anywhere. A proton has a sort of intrinsic spin associated with it. Again, the spin is not literally the proton spinning, it's sort of more like a mathematical artifact, mathematical property, and it has a magnetic moment and an angular momentum. And because of there being, there are different states present, and when you apply a magnetic field, an external magnetic field, this is the sort of schematic of the proton, of the proton NMR, of any NMR experiment, in fact, to be honest. And if you apply a magnetic field, there is splitting of energy states. And this kind of splitting of electronic energy states, rather, sorry, not electronic, these are like nuclear energy states in the presence of a magnetic field, is known as the nuclear Zeeman effect. For those of you who have already read about this, my apologies. For those of you who have not, splitting of energy states in the presence of a magnetic field is known as Zeeman effect, and splitting of fields in the presence of electric fields is known as the Stark effect. So energy states tend to split when you apply a field. And the simplest practical example of this is, for example, when you've done your crystal field theory in inorganic chemistry. You remember under an octahedral environment, the sort of 5 degenerate d orbitals split into T2G and EG transforms, right? That's an example of splitting under the application of a ligand field. And this is just another kind of splitting in the principal field. So effectively, if there is splitting between states, as is obvious, there'll be differential population between the different states, depending upon sort of the statistics of the particles. And there'll be absorption from one field, from one state to another, from the ground state to the excited state, if you think about in terms of kind of the Frank Condon picture that I showed yesterday. And this absorption actually occurs in radio frequency. Radio frequency meaning that the wavelengths involved are almost of the order of radio waves, which are very, very, very long. And you can have a look at the absorption, and there's a lot of synthesis going on, a sort of mathematical synthesis going on before you get the sort of final data. But again, you can actually measure something which is known as a chemical shift, and the presence of these chemical shifts can actually tell you about the chemical environment around the proton. So this is one of the probes which can actually probe local atomic environment. So if you want to probe the proton, you do NMR. If you want to probe the lithium, there's a different form of NMR, so on and so forth. But this is one of the techniques which can be used to probe atoms directly. And to be honest, there are multiple modern developments of the technique which are used. In fact, NMR is a very, very, very vast area of research. You get to read about it all the time. Another thing that you must keep in mind is that by looking at this, you can find that there are magnets, and you need to put the sample in between the magnets. And this requires very, very, very high magnetic fields. Like I was just quickly taking a look at the values yesterday. And the thing that I noted was that for NMR, you need 10 to 20 Teslas worth of magnetic field. And the Earth's magnetic field is 10 to the minus 4 Tesla. So such strong magnetic fields are usually generated by electromagnets. And those huge electromagnets need a lot of liquid cryogen to keep them cool. So it's a very expensive kind of instrumentation. Not all labs have them, but good research labs do have them, and they can be used to provide a plethora of information about chemical systems. So NMR is the kind of tool that you would want to go to if you want to look at sort of atomic level information in systems. Just a quick follow-up, like I mentioned, MRI is actually dependent upon NMR. Again, I hope none of you have to get it, but if you know anyone, and if forever, for whatever reasons, you need to get an MRI done, it's basically imaging based on nuclear magnetic resonance. And now that I talk of imaging, because this is a part of a self-development program, I mean, it's important that I mention that imaging is a fast developing area in spectroscopy. For those of you who have an interest in sort of basic data transformations and things like Fourier transforms, Fourier synthesis, this is an area that you can consider as a future career, because if you know how to generate images from spectroscopy data, you have things like MRI, you have things like computed tomography, and so on and so forth. These are very, very, very hot areas of research in the industry as well as in academia. Right. Now that I've mentioned a bit about NMR, there's just a small bit of case study that I want to mention of a real life application of NMR. I don't know a lot about NMR. At some point of time, I had the opportunity for doing a little bit of studying this binding of this kind of a small molecule. This is known as metformin. It's a sort of anti-diabetic drug. And as a part of a collaboration with the theory group in our department back in ISC led by Professor Biman Bakchi, we were doing a kind of measurements of this molecule binding to the DNA. And because there's a small molecule, it's easy to characterize it using NMR. So this is the kind of, NMR spectra. So this is chemical shift in delta ppm, and this is absorption. And depending upon the type of protons present in your sample, you get peaks. For metformin, due to reasons that I don't want to sort of go into right now, there's only one equivalent proton, chemical proton. So this is why it gives rise to one peak in NMR. If you have multiple peaks, this one is for D2O, which is the solvent. If you have multiple peaks, then that means you have multiple protons in different environments. This is a kind of, a real life application of NMR spectroscopy in characterizing molecules. There are millions of others in the literature. And another sort of more complicated experiment, remember I'd spoken about diffusion yesterday. That's one of the molecular phenomena that you want to sort of probe by spectroscopy. So there's this sort of two-dimensional NMR. Again, the thing is a bit complicated, but if you're interested, do go and read about it. And two-dimensional NMR is known as techniques known as diffusion ordered spectroscopy, or DOSI, can be used to actually find out diffusion coefficients of molecules too. So effectively, this is delta ppm versus diffusion coefficients, the two-dimensional plot. And depending upon the point in space which corresponds to your molecule, you can find out the diffusion coefficient. So NMR, the example that I've said here, this is the one that I'm trying to push through, is that NMR can be used for probing local structure as well as bulk phenomena like diffusion, depending upon the complication of the experiment that you're doing. So, my apologies for quickly talking through a lot of things, but again, this is a kind of a pit stop. Just wondering that of the things that I've talked about so far this morning, do you have any questions till now? All right. So I'm assuming that no one has any questions on this, on NMR?
Well, I might ask one. You see, it's actually probing the nuclei, if I got it right.
Right.
Now, typically chemistry happens beyond or in the electronic cloud level, not at the nuclear scale.
Correct. Right.
And relatively, there's a big difference between, if you look at the atom, the relative size, I mean, the nucleus is quite small. So it is probing very small area. And so, but it is possible from, as I gather from seeing your view graphs, to get some idea of the chemistry as well, not just the elemental composition from NMR. Did I get it right?
Exactly. That's thank you, Professor Shramaza. That's a sort of interesting point to raise. That effectively one would not talk about nuclei in sort of practical chemistry, because chemistry is more associated with electrons. Nuclei is the sort of domain of nuclear physicists, or those who work with radioactivity and that kind of stuff. However, as it happens, it's sort of like an elegant design of experiment. The protons are ubiquitous in chemistry. Like protons are everywhere, right? You study proton transfer, protons this, protons that. And protons effectively are very, very, very simple nuclei. So if you use something, a kind of a nuclear probing method to probe a proton, that's effectively getting an idea about chemistry by using a technique for probing nuclei. That being said, when you move on to more complicated nuclei, such as lithium, aluminium, so on and so forth, you can still do NMR, but the kind of information that you get becomes a little more complicated, and then you can study other kinds of things like nuclear diffusions and so on, which maybe sometime does not look directly, does not appear directly as chemistry to the eyes of a chemist, but protons, definitely chemistry using nuclear techniques.
Thank you. Thank you for clarifying.
Sure. Thank you. So if none of you have any questions, again, I didn't say this, but please do feel free to pop up questions in the chat box. I have these kind of short stops in between, where I'll be happy to sort of discuss if you have any questions or any suggestions, comments on what I'm talking about.
Dr. Samasdar, sorry
Yes,
for the
please.
interruption. One question is there from Orindam Roy. He is asking how NMR works in materials. This is
Thank you, Dr. Roy, and thank you, Orindam, for raising this sort of very interesting question. How does NMR work in materials? Now, sort of in trying to answer this, the way that I would try to defend this question is that materials effectively also have, let's say, bonds, right? And there may be certain kinds of materials where protons play an important role. Offhand, the thing that comes to my mind, Arindam, is, for example, membranes, which, for example, those of you who are aware, so there's this kind of green technology in cars developing, right? So there are things known as battery operated cars. I think Mahindra has one right now. There's Tesla, which is the sort of the posh one. And these are battery operated cars, and batteries have things known as separators inside them to separate the cathode and the anode. Then, for example, for those of you who are interested in fuel cells and hydrogen technologies, there's hydrogen operated cars too. The one that's there in the UK is known as a Toyota Mirai, and it runs on hydrogen. Why are these important? Because they run on green energy and they don't depend on fossil fuels. So an important part of these fuel cells are membranes, which are used for movement of ions, but not movement of electrons. So if you're looking at movement of protons, proton transport membranes, which are very common in these kind of hydrogen technologies, that's effectively an area where there's a lot of investment in the materials, sort of material science community, industry, in developing these membranes. And in order to study these membranes, if you're studying protons, NMR is a sort of indispensable tool, isn't it? For example, if you have some time, just look up proton sort of poly. They are known as PEF, PEMFCs, I think, proton exchange membrane fuel cells. Look up the websites of maybe Johnson Matthey or some of the sort of popular catalysis companies in the world, and you'll be able to find the amount of effort that they put in sort of characterizing these materials, and NMR is an important part of it. Thank you.
A few more questions are there in the chat box.
Please, Dr.
Orko Saha has asked that what is the difference between IR and Raman spectrum?
Sorry, thank you, Orpon, for this question.
Anirban, before that, I think there is a related question by Purba, related to NMR.
Yes,
so it might be more pertinent here, and
yes.
he can take the other question after that.
Please, Dr. Roy.
Purba Bandyopadhyay, she has asked why we use benchtop NMR spectrometers.
That's a very interesting question. Benchtop NMRs. Actually, to be very honest with you, Purva, I have never used a benchtop NMR before. So benchtop NMRs have apparently become popular in recent times. The sort of NMR spectrometer that I had used during my PhD time at the Indian Institute of Science was a sort of regular NMR where you had these kind of huge electromagnets, and there's this, you had to take liquid. I mean, to be honest, I never did a lot of NMR because I was not in the kind of synthetic organic chemistry area. But I remember there was this huge magnet, and one needed to fill up liquid, I think it was liquid nitrogen, because the liquid helium was inside the magnet. It's a closed cycle, I think, cryostat. But yeah, you needed to fill up the cryogenic liquid and everything to keep the NMR running. So those were huge instruments. Now I know that there are that very, very, very good point. There are benchtop spectrometers, and there is even benchtop NMR that is coming into the market nowadays. I don't know anyone who has used it. And as a sort of educated guess, what I would say is that if you have benchtop magnets, you'll not have as high fields as, let's say, kind of regular electromagnets in NMR. And that may compromise with the kind of resolution. Like, I've not really talked about it. Do read up about it. So NMR resolution, it's talked in terms of frequency. So a good lab will have a 700 megahertz NMR. A sort of a slightly older lab might have a 400 megahertz NMR. So what is this frequency? Read on about it. And the frequency, the sort of more well-resolved spectra you get. So I spoke a lot, but the kind of, in a nutshell, my response would be benchtop NMRs may not have as good resolution in spectra as in, regular.
So in that case, if it might be used for cases where you do not need high resolution.
Exactly.
And what could be some possible examples or materials or?
That is another excellent question. Again, offhand, it's a bit tricky to say. But for example, when do you need resolution? When you sort of closely spaced peaks, right? So what is spectral? Well, apologies, I've not really talked about spectral resolution till now. That's an area that's also quintessentially important in spectroscopy. But again, that's a bit advanced. So resolution means that if you have a number of peaks and they're sort of all clumped together in a kind of a broad peak, then you're really not able to identify them separately. But if you are able to sort of space them well on a high resolution spectrometer, then you can identify each peak separately. So let's say you have a material, like for example, the kind of molecule that I showed. It's not a material per se, but it's a molecule, such as the previous one. Something like this, where effectively all these protons give rise to, they're all chemically equivalent per se in the local area. So it has only one peak. So if you're studying only one peak in your NMR, then a sort of benchtop spectrometer might be useful. And it is economically viable because I'm sure many labs are able to afford a benchtop spectrometer because it costs definitely much less than a regular spectrometer. So if you know materials which just have one proton, not very complicated structures, go for the benchtop one because it involves much less resource involved in running the experiment.
So Purba asked something, perhaps pointed out that in your own experiment, you could have used the benchtop one if it were available.
Guilty as charged. Very, 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 very interesting comment, Purba. I'll be very honest with you. Sort of the advantages of doing a PhD in a kind of a slightly more old institute is that you have access to these resources, and we are extremely privileged. In fact, I should honestly admit that I did my PhD in IISc, and it had a lot of excellent resources, and I'm really grateful for that. They didn't have a benchtop one at all. If there was a sort of condition that, okay, you run a benchtop spectra if you have a simple molecule like metformin, but if you have a molecule like cyclodextrin, go for the sort of regular spectrometer, then I would have definitely chosen the benchtop one. But when you get the regular one for free, then yeah, you just choose that one.
So the question that is revealed to answer is difference between IR and Raman spectrum.
Right. Thank you very much for asking this question. This is basically, the difference is in two regimes. So first of all, IR is essentially an absorption phenomenon at the physical scale, at the physical way, if you would like to differentiate. IR is absorption of radiation. Raman is scattering of radiation. There's a difference between absorption and scattering, first point. And the second thing is that the way that the sort of quantum chemistry of vibrational modes work is that if the vibrations involve a change in dipole moment, then the system is IR active. For example, if you have a carbon-oxygen bond, such as those which are present in carbonyl compounds, those of you who are from an organic background, you have very strong IR absorption spectra centered around 1600 centimeters inverse. However, if it is an oxygen-oxygen bond, then there's not much change in dipole moments, right? I'm assuming that you're aware of dipoles, dipole moments, and so on. So in those kind of cases, which are dipoles changed silent, Raman scattering gives rise to signals. Why does that do? The physics of Raman effect is pretty complicated. I've not really gone into it, but instead of change in dipole, as is the case in IR, Raman involves a change in polarizability. Now, what is polarizability and how does it differ from a dipole? It's a bit more complicated thing. Polarizability is a tensor. Go and read about it in any standard spectroscopy, sort of physical spectroscopy text. But yeah, in a nutshell, Raman is scattering and deals with vibrations which do not involve a change in dipole. IR is absorption and deals with vibrations that involve a change in dipole.
Thank you, Dr. Somastha.
Thank you, Dr. Roy, and thank you, the audience, all of you, for such interesting questions. Do keep on asking them, and even if I'm sort of using up a little extra time, I'll definitely sort of speed up to the end. There's not much more that I want to talk about. Just quickly coming back to, again, our guiding map. So now we have NMR sort of encompassing this entire area, right? Starting right from atoms to bonds to molecules to local molecule structure. In fact, this is an area that, still a bit gray. I mean, NMR can be used to understand these kind of large scale structures too. There's a lot of biomolecular NMR, and people do this kind of work, but for the sake of, let's say, staying, within the sort of main domain of applicability of NMR, this sort of spans this entire area. And there's a very interesting thing that I would like to point out here. So, yesterday we have talked about wavelengths of radiation, right? And sort of a way that we often tend to think is that the wavelength of the radiation is kind of like the length scales that we are studying. However, if you think in that way, now this is valid for X-rays because of X-ray wavelengths being close to crystal spacing and so on. I'll discuss this a little later, but keep in mind here that you're probing a proton, which is, extremely small. I mean, I don't have offhand the dimensions of a proton, but I assume that it's lesser than a nanometer and angstrom level. And what you're using is radio frequency radiation. That's high wavelength radiation. So be aware that don't try to sort of go into that wrong kind of pattern recognition system where basically if you have, IR wavelength is this much, so it sort of probes bonds which have this kind of length scales. This does not always work. So the probing radiation, the wavelength of that depends actually on the kind of differences in energies involved, if it's an absorption kind of phenomenon. So it's not the length scales of the phenomena that you're studying. If it's diffraction or scattering and other kinds of optical effects, then you're more or less in the domain of the wavelength of probe being sort of commensurate with the sort of length scales that you're trying to study. Right. So with this,
thank you. That was a very important footnote to make. Thank you.
Thank you, Professor Shamazar. Yes. Thanks. So now we sort of move on to the next world of things. So we now sort of, we are now the only thing left is this. So large structures. So atoms combine to form bonds jiggle and wriggle, they combine to form molecules sort of cluster together to form local chemical environments, and these sort of grow into a large scale, and you have crystals, and crystals effectively are the ones that you can see in sort of real life. These beautiful crystals of precious stones, so on and so forth. So this is the area that we're still left to touch. And so I'll come to this now. It's attaining, larger structures. So before we start, just a sort of, again, a kind of recap to what is known as the world of symmetry. Now, I had pointed out yesterday that the symmetry properties of molecules are extremely important. And I'd also mentioned that a mathematical understanding of symmetry is, indispensable. It's an absolute requirement if you want to understand large-scale structures. Why? Because knowledge of symmetry makes things very simple. So, the sort of branch of mathematics, again, for those of you who will be taking up, who will be sort of doing a little bit more reading on crystallography as a part of your self-learning program, you'll probably learn about this a little bit more in detail from textbooks. But the branch of mathematics that deals with symmetry is known as group theory. Group theory has applications everywhere. It's a complicated area, and to be honest, I'm not an expert of group theory, even though group theory is very, very, very important in spectroscopy. But I'll just give you an overall flavor for the kind of theoretical approach. So when you have a molecule like water, this is water, right? So there are some symmetry properties associated with water. For example, this is a C2 axis, meaning that if you just take this axis and rotate the molecule, I think I have a copy of the molecule here, so I'll just be able to maybe, yeah, so let's say, for example, I'm not sure if you can see this. So this is water, right? And if I just take this molecule and rotate it 180 degrees, you still get the same kind of molecule, right? So this is known as C2. This 2 meaning 360 by 2 rotation. If you have a more complicated molecule like benzene, something like this, if I take this axis and rotate it by 60 degrees, that is 360 by 6, you still get the same molecule, and that is known as a sort of C6 axis. Anyway, so water has a C2 molecule and it has 2 planes of symmetry. What do I mean by planes of symmetry? For example, if this is the molecule, and if I put a plane like this sort of divides us into 2 mirror images of each other. Similarly, if I put the plane like this, it's sort of slicing the molecule. You again get 2 mirror images of one another, right? So these are known as sigma planes. Now, I've really sort of saying this at a very simple level, But a combination of these kind of symmetry elements can be used to identify what is known as the point group of the molecule. Right. So if you remember, right, when I'd spoken about vibrations, I mentioned that if you know the point group of the molecule, point group is a mathematical quirk. You can read about it in group theory, but this is very important in terms of molecules. So if you know about point groups, which are associated with molecules in general, you can predict vibrational modes, so on and so forth. Now, however, note that when we are analyzing molecules in general, we don't talk about translations, right? Because the molecule is, even if it's sort of moving around in space, I'm not really concerned if I'm studying this at a molecular level. So I'm interested in only symmetry elements associated with the molecule in itself. However, when this kind of a water molecule packs itself in a crystal, and this is essentially ice, this is the crystal structure of ice. There are many structures. I took this from the materials project database. So now that I've mentioned this, the materials project database is an excellent resource for finding crystal structures. I'll just come back to this a little later. But yeah, if you pack this in space, then you find the same molecule sort of repeating itself at certain patterns over an area. So this brings into effect what is known as translational symmetry. So you have a molecule here which has this kind of C2 and sigma properties, but go a little bit forward and you'll find this molecule. Go a little bit this way and you'll again find this molecule. And this kind of a patterns will repeat all over space depending upon how big a crystal you have. So this sort of introduction of translational symmetry to a molecule actually makes the mathematical transformation from point group to space group. Again, points group, space group, these are essentially mathematical constructs. Read about them. And however, the knowledge of space group, just like a knowledge of point group is important for understanding vibrational modes in spectroscopy and molecular orbitals in general, a knowledge of space groups is essential for understanding crystallography. So the thing that I've sort of set here is actually known as a unit cell. So this is what is known as basically a unit cell. It's defined by 3 vectors, A, B, and C, and 3 angles, alpha, beta, and gamma. And these vectors, these are sort of, you can think of them as like basis sets. For those who have done quantum mechanics, you can sort of deconvolute functions in terms of basis sets, right? So in crystallography also, these basis vectors span, space, and they repeat to give rise to crystal structures. And depending upon, the values of alpha, beta, gamma, and A, B, and C, you get what are known as 14 types of Bravais lattices. Bravais lattices, again, are a sort of artifact of mathematics. They're not sort of originating from crystallography in general, but they are essential for understanding crystallography. So a combination of these different kinds of Bravais lattices, 14 types of Bravais lattices with point groups. Molecules have totally 32 point groups. So these two combine together to give rise to space groups, and there are 230 space groups. So you can imagine how complicated the world of crystallography is. A lot of information in one slide. My apologies for this, but just to sort of draw your attention to some basic reading on this, if you're interested. Understanding Group Theory in Chemistry, there's this excellent book by David M. Bishop, which deals with group theory and chemistry. There's also a nice book by Cotton. You can refer to that as well. Understanding Symmetry Properties in General, there's another excellent book called by the Russian author Lev Tarasov, known as The Amazingly Symmetrical World. I'd really recommend you reading this book if you can find this in your library. Tarasov is an excellent writer. His book on calculus is also fantastic for those of you who are interested in math. But
that book is available free online. It is downloadable.
So there you go. So do spend some time. It's not mathematical. It's just showing that symmetry, how it appears everywhere in nature. So this is a very, very, very important, a sort of one that I really recommend for your sort of pleasure reading at your, any time of convenience. Right. So without wasting, more time on this, this is the sort of broad picture of transformation from molecules to crystals. One quick comment here. This is the way you understand crystals in terms of unit cells. Now, apart from A, B, and C, there are also something known as sort of crystal planes. Okay, so for example, here what you see, this kind of I've taken this image from Wiki, but you find this in any standard crystallographic text. So these are basically a plane sort of connecting the 3 vertices of this kind of a unit cell, right? So effectively, these are known as crystallographic planes. They will become important in the next slide. Now, how we represent these planes like I've told you about ABC and alpha, beta, gamma, right? So there's another set of important parameters which are known as HKL. So, you know, for this plane, you see that it makes an intercept of 1, 1, and 1 on the 3 axes, right? So these planes are defined as A by 1, B by 1, C by 1. So notice the kind of reciprocal relationship between A and these A, B, and C, and these 3 numbers 1, 1, 1. So these numbers 1, 1, 1 are known as Miller indices, and they are reciprocal. They are sort of have a sort of reciprocal relationship with the basis vectors here. The word reciprocal is important in crystallography, and I'll come to this a little bit in the next slide. So now that you know about crystals, following this, let's move on to a little bit of crystallography. Again, X-ray crystallography is a huge area of research. You can take 1 semester's worth of course on this, and you'll find excellent resources on the internet. But I'll just try to sum up, do justice to this in 1 slide. And 1912. So the book that I would recommend is Christopher Hammond's Basis of Crystallography and Diffraction. It's an IUCR text. So it starts off with a very nice example. In 1912, Max von Laue had studied, you know, diffraction patterns of zinc selenide crystals, which probably have a kind of 4-fold symmetry present. So these are what are known as diffraction patterns in crystallography. Okay, so as you can see here, this is somewhat like a square, isn't it? So you can see what is known as a kind of 4-fold symmetry present. If this is the axis going into the sort of screen, then if you rotate this, you'll be able to find a symmetric structure. This was Max von Laue's observation in 1912. Later on, William Lawrence Bragg and his son, father and son Bragg, they were also able to identify that, you know, these kind of diffraction patterns form, you know, something like an ellipse. I mean, it's not very sort of clear here, but if you just look into the text, you'll be able to find that there's a sort of elliptical pattern in between these kind of diffraction patterns, and that they're not ideally circles. And the greatness of the Braggs were that they were able to identify this, sort of not identify, rather they were able to reconcile this to the kind of patterns which are observed if you reflected light between 2 planes which are closely spaced to each other. And this started the revolution in crystallography, the emergence of the Bragg laws, and, you know, resulted in Nobel Prizes for Max von Laue in 1914 and father and son Bragg in 1915. So remember I mentioned that NMR was one of the few techniques which had 2 Nobel Prizes for method development. Crystallography has again 2 Nobel Prizes for method development, and apart from this, there have been n number of Nobel Prizes for, you know, developing crystal structures. Some of the common ones that come to mind, for example, developing structures of proteins. I think myoglobin, hemoglobin. Myoglobin was Kendrew, and I've forgotten the one who solved the structure of hemoglobin, but they've all resulted in Nobel Prizes. So you have a large number of Nobel Prize lists in crystallography in general, but these 2 were for pure method development. So it's coming, sort of bringing your attention back to this. This is the 1912 picture of zinc selenide diffraction, and this is the 1952 diffraction pattern of the double helix structure. This was reported by the group of Cavendish Labs in Cambridge, right? So Rosalind Franklin.
The famous plate number 51, I guess.
Exactly. That, yeah. Thanks. It's just remember, this is the famous plate 51, and this sort of started, you know, the solution of the structure of the double helix. And if you are there in Cambridge, you do see this plaque. The structure of DNA was determined here. So this is the old, if you're there in Cambridge, you'll find that the old physics department has shifted. I have been here, thankfully. So it is nice standing in front. This is the old building. I don't think there are labs here anymore, but this this building is marked by this plaque saying that, you know, Francis Crick, Watson, and Rosalind Franklin were responsible for discovering the structure of DNA, you know, in this building. And if you want to read about this, just as a sort of, sorry, taking your time, but just can't help but share this, the story behind this. If you're a fan of Watson and Crick, there are 2 books that are must reads. One is What Mad Pursuit by Francis Crick, and the other one is The Double Helix by James Watson. And it tells you about the sort of tremendous competition between Watson, Crick, and the others at Cambridge, England, and Linus Pauling back there in the US, and how one almost beat the other to a Nobel Prize, but ultimately it sort of went on to, you know, to Watson and Crick. Right. So stories aside, coming back a little bit more on, so being a little more serious now. crystallography involves a lot of good physics, maths, everything. And it's not something that I can sort of, it's not something that, to be honest, I understand extremely well. And it's not something that, you can explain in a slide, but just I've pointed out a few things. So there are some conditions of diffraction. Now, first of all, I want you to recall scattering, diffraction, and interference. How do they sort of differ? Very broadly speaking, diffraction means basically there's a sort of wave source that passes an obstacle. Let's say there are slits, and it sort of bends around the obstacle, and the obstacle becomes a sort of secondary source of waves. So this is diffraction, right? And scattering, essentially, I try to think of it in this way, that scattering is the kind of atomic or particle level explanation of diffraction. That is, waves come, and if you think of light as waves come and hit a particular obstacle. There is exchange of kinetic energy, there is change in the wave vector direction, and thus a primary wave hits an obstacle and there are secondary waves generated. You can think of it in terms of particles or waves, but scattering in one way is a kind of molecular, you can say like particle level or atomic level explanation of diffraction. Now coming to interference, if you would recall a little bit, so do read about these things when you're reading about when you're developing your self-learning in crystallography. If you remember interference from your high school physics, so there was something known as a Young's double slit experiments. So light passed through very closely spaced slits. Those slits became sources of secondary waves, and these waves then sort of in one sense, crudely saying, mixed with each other, and where the kind of intensity is matched in phase, there was an increase in intensity. Where they were not in phase, there was a sort of decrease in intensity, and there were conditions for interference. And these are the three sort of basic physical phenomena which are very, very, very important if you want to understand crystallography. Sorry if I spoke too fast through this, but discussing these would take a lot of slides and a lot of physics. So I really don't want to go into this, but I just wanted you to point you out that sort of clear your concept in this domain before you move here. Now, if you move to crystallography, back to crystallography, when there is diffraction from a crystal, there are wave vectors going and hitting those crystal particles, and there are a set of conditions which are known as sort of like law conditions of diffraction. And these conditions are sort of manifested here. So each wave vector interacts with kind of like these basis vectors of the crystal lattice, giving rise to, kind of a set of vectors which are sort of known as these HKL vectors or the Miller indices vectors. And these, you have these kind of basis vectors forming your real lattice. And after the law conditions are satisfied, you get a set of Miller index kind of vectors which form a different kind of lattice. So remember, the HKL is sort of like a reciprocal relationship to A, B, and C. So the lattice that you get there is actually known as the reciprocal lattice. And the crystal lattice and the reciprocal lattice are again related by mathematical transforms. Reciprocal lattice is a sort of very sort of abstruse mathematical object, but it is essential if you want to understand crystallography. So this is the sort of foundational theory in terms of conservation of momentum and so on of crystallographic diffraction. However, the sort of more elegant consequence of this was what was identified by Bragg. And this was a success in seeing this. Is that, for example, if you think of interference, this is the picture that you've probably all seen, even if you've not read about law, is that there are, two planes of crystals, the spacing between them is d. There are two sets of waves that come in, and so they get kind of reflected, if you will. The one reflected from here and the one reflected from here, this is the angle theta. So, and if this is d, then the path difference between these waves is 2d sine theta. And if the Bragg condition is if n lambda is equal to 2d sine theta. So if you have this, if it's an integral multiple of the wavelength, then you get to see constructive interference, and then sort of peaks come up in the spectrometer. So this is essentially Bragg's law. Again, my apologies, just like the previous slide, a lot of information here. Sort of the take-home points would be scattering, diffraction, interference, crucial physical phenomena behind crystallography, law conditions of diffraction, foundational theory of crystallography based on conservation of momentum and scattering of X-rays from crystals, defines what is known as the transformation from the basis vectors ABC to the reciprocal lattice vectors HKL. Following this, Bragg's law is a very elegant understanding of this kind of diffraction in terms of reflections from parallel planes. And what we know is that the X-ray wavelength lambda is very comparable to the interplanar spacing in crystals, D. They're of the order of angstroms. And thus, X-rays are sort of naturally chosen to probe order in crystals. Having said this, I just want to draw your attention back to a comment that I made earlier. When you're looking at spectroscopy, depending upon the type of phenomena that you're studying, be careful about mapping length scales of the probing radiation to the length scale of the system that you're studying. NMR, huge length scale of radiation, huge wavelength, but probes atoms because it's absorption, and the length scale converts to energy in NMR. X-rays, based on scattering and diffraction, different sort of physics involved. So the length scales of the radiation are very commensurate to the sort of length scale of the structure that you study. Having said this, I'll just move on to the next slide, which is the sort of last slide in this. Lot of information again, sorry. A few words about instrumentation, because if I don't mention this, it would be like not doing justice. So there are two ways of doing crystallography. You take a sort of crystal and powder it. This is, for example, I come back to lithium cobalt oxide. This is the powdered version of lithium cobalt oxide, and this is the single crystal structure of lithium cobalt oxide. Essentially, both of them give you the same kind of information. But how do you do an experiment if you're doing crystallography work? So if you take powdered X-rays, it means that the crystal is ground up in such a way that multiple Bragg planes are exposed at the same time, because it's nicely ground. And then what you do is you put it in a powder X-ray diffractometer. These are instruments which are present in most research labs around the world. Powder X-rays are very important. For example, if you're going to take up a career in pharmaceutical industry, where basically interaction of drug development of drug molecule composites, you take a tablet, grind it, and put it under this powder X-ray, X-ray diffractometer, and look at how the crystal structures are. So this area is more of interest to those who are planning to take up a career in sort of pharmaceutical materials. Powder X-ray diffractometer does a data collection which is known as Bragg-Brentano geometry. Effectively, you do something like this. You vary the theta angle and look at diffraction intensity. So you have a plot of intensity versus 2 theta. I'll show you the plot in a while, and you get a powder diffraction pattern. It helps you identify what was there inside. On the other hand, if you have a single crystal, then you mount it in a different kind of spectrometer, which is on a single crystal diffractometer. The difference between this and this is that because this is well ground and there are many sort of literal single crystals, many faces are exposed. Here what happens is, because it is a single crystal, only one face is exposed at a time. So what you have to do is you have to slightly rotate the crystal, and this is done by what is known as a goniometer, and then look at diffraction patterns coming up here. So this is the kind of diffraction pattern that the great crystallographers started with. Something, those who are the sort of pioneering fathers of crystallography, pioneering pyramids of crystallography. So you get these diffraction patterns by rotating the single crystal. There's a lot of mathematics involved. I won't even think about going into detail, electron densities, etc., etc. There were times when you had to read, if you're a sort of professional crystallographer, then you have to pay attention to all these things. Otherwise, a sort of detailed analysis with, it requires years of experience and knowledge, to be very honest with you. But a detailed analysis of this gives you an end product, which is a crystallographic information file. And this is the sort of information that you and I, as let's say practicing sort of spectroscopists or material scientists would be interested in. You want to go into this only if you want to take up a career in crystallography, single crystallography. And this contains all the information. If you have this file, you can predict the powder diffraction pattern. If you have the powder diffraction pattern, you can also predict the single crystal. And those are methods known as refinement, but they are a little bit more complicated than the other way around. Now, having said this, I've sort of reached the sort of end of crystallography, but I would just want to show you something here, which is, if I may, I'll just sort of, yeah, there you go. So this software is known as Mercury, and it helps you actually visualize crystals. So the one that you're seeing here is essentially lithium cobalt oxide. There are different ways that you can sort of, if I put on just label atoms, so you can see that. Let me just first of all show just the kind of the basic unit. So you have lithium, oxygen, cobalt. They come together and they form what is known as the kind of unit cell of things. So this is somewhat similar to the unit cell, where lithium, cobalt, oxygen, they pack in a particular kind of, so if you keep on rotating this, you kind of end up looking at the symmetry at some point of time. And then if you want to look at, higher levels of packing, you take this and voila, there you go. This is the sort of extended crystal structure. And the elegance of this thing is that, of looking at crystallography in this way, is that if you look at it in certain kinds of axes, they're sort of like huge population of things. But if you just know where to look or what axis to look at, it sort of resolves itself to, something very, yeah, you need to play with this a little bit, but yeah, you can just sort of simplify the view, the kind of view, so that you can find out which symmetry elements are in it and so on and so forth. Now, this particular package is known as Mercury. This kind of information, for example, is what is a crystallographic information file. It's available in most cases over data reported in the literature by scientists, and if you have this file, why I wanted to show you this, you can also predict powder diffraction patterns. So this can be done in softwares. So I just go here and I click on powder pattern. And what you have here is essentially your powder X-ray diffraction or Bragg. So if I really took this single crystal, and really nicely sort of took a kind of mortar pestle, grounded it, all faces would be explored. And then if I just studied intensity as a function of 2 theta, then you have these kind of peaks coming up. All of these peaks correspond to certain planes which are present in the crystal. And taking a look at this, you can identify, the type of crystal that is present in the system. So this is all about, SIF files, powder patterns, visualizing crystal structures, and just wanted to give you a flavor to sort of, the kind of things involved in crystallography. Now, if I may, I'll come back to the main slide, and just as a sort of follow-up, this is some useful information that you might find handy. No need to again copy this down. I'll share these slides. For viewing structures, the software that I used, Mercury, this is available freely from this database. You can download it in your computer and just have a look around with it. If you want to download crystal structures or SIF files, there's this thing called the Open Database of Crystallography. Look this up, type in something like ice or sodium chloride, download the SIF file and take a look at how the crystal structure looks like. Apart from this, this is something I mentioned earlier. There's this excellent sort of consortium of information on chemistry, which is known as the materialsproject.org, which is run by, I think, the Lawrence Berkeley National Lab in the US. And this database also has sort of SIF files and etc. information, a lot of other kinds of information for almost all kinds of chemical systems that you can think of. So yeah, these 3 sources of information would be useful to just sort of have a play around when you have some free time with your computer. And this brings me to a case study. I've talked only about X-rays, but this is this nice bit of work which was done from the Bhabha Atomic Research Center in Mumbai, the Institut La Langevie in France, and there were 1 or 2, and there was also another group in England. I think this is based on Queen Mary University in London. So this is a crystal structure. It is known as perovskite. Perovskite is a unique form of crystal structure, and this is calcium titanium. So you see a calcium here, a titanium sitting here, and oxygen sitting here. So this is a crystal structure, and if you do an X-ray diffraction, you'll be able to identify the crystal structure. Now, these are the people who worked on this. This was a report in 2019 in the Journal of Physical Chemistry C. So again, for those of you, my apologies for those of you who know, but for those of you who don't, this is a way in which we sort of represent literature in chemistry. So there are different formats of doing this. Maybe just have a read about them. This kind of representation of reference is known as American Chemical Society format. This is the name of the journal, Journal of Physical Chemistry C, in a particular abbreviated form, which is well defined. This is the year in which the article was published. This is the volume number, and this is the page number which contain the article. So if you know this reference in this particular format, it will become very easy for you for practicing, people who work in the sciences to actually get back to the article that I'm referring to. Sorry for this quick aside, but yeah, just wanted to sort of let you know about references. Coming back, so if you have something like this, you can use X-rays. But what these authors did was that they sort of used a different kind of structure, which had this copper system, and they had a kind of guanidinium structure, which the framework was made of guanidinium, which contained oxygen, carbon, nitrogen, and deuterium. Now, the problem here is that if you have these kind of low atomic number elements, such as carbon, nitrogen, deuterium, X-rays don't really diffract that well. The reason being, it's sort of the way X-rays interact with matter. If high electron densities are present, X-rays diffract well. But if they are not, these have low electron densities, they have low number of electrons. So then X-rays don't diffract that well. But neutrons, which are neutral, diffraction physics is the same, whether they're neutrons, X-rays, electrons, and so on and so forth. But neutrons can be used to find information about the structure. Another important thing is that what these people did was that they took copper at this site, and they then replaced copper with, for those of you who are aware of the periodic table, like manganese, iron, cobalt, nickel, copper, zinc. So they sort of had a play around with these kind of 3D transition metal elements and replaced this copper with manganese, iron, nickel, zinc. I think they did manganese, iron, and nickel. And those are very close to each other. And because they're very close to each other in the periodic table, their electron numbers are very same and their X-ray diffraction sort of properties are similar. But their neutron diffraction properties are different. So they use neutron diffraction. So what I'm trying to say here is that instead of X-ray diffraction, you can also use neutron diffraction, given the electron densities are low, such as you have proteins which have a lot of carbon, hydrogen, oxygen in them, or if you have similar X-ray kind of scattering centers present. Right, so this is a bit about neutron diffraction. As a follow-up to X-ray diffraction, you can actually take this further to understand electron diffraction and so on. I now come to the end of the crystallography section and almost towards the end of my talk. But again, I'll stop here because I admit I'm guilty as charged that I've spoken about a lot of things which are somewhat complicated too. So happy to take any questions or comments or doubts that you may have at this point.
Dr. Samasdar, a few questions are there, and most of them are from Purva Bandyopadhyay.
Yes, please.
So she is asking a question: what is the better way to detect and quantify micro and nanoplastics in any sample?
Thanks, Purva, for this question. I mean, assuming plastics that they are polymers, so first of all, the kind of linkages that are present in polymers, so let's say they're, I don't know, sulfonates or other kinds of organic polymers. The first sort of technique of choice would be IR spectroscopy, because you know that these bonds are vibrating, and assuming they involve dipole change. In case they are not IR active, if you know this, it'd be worth doing some Raman spectra on that as well. Now, this is an important area that, you know, these kind of polymers, they are also so in one way condensed phases. So they may have some ordering, right? For example, glass is a polymer. It is sort of, you know, it's a kind of a transition state between amorphous and crystalline. So I'd suggest maybe, because it's polymers, again, organic polymers, maybe neutron diffraction if you want to have some idea. And obviously another important thing is, because you spoke about micro and nano plastics, there are length scales involved, right? So another important technique would definitely be sort of microscopy. I've not talked about microscopy at all, but you know, if you would want to do some scanning electron, transmission electron microscopy to understand structure, and if you want to, for example, characterize the topography, then you'll probably be well off doing things like atomic force microscopy or scanning tunneling microscopy. Sorry, there was a sort of large set of techniques that I spoke about, but as I'm sure you'll appreciate by now, that you know, you can use different kinds of techniques to find out different aspects of, you know, information about the system that you're studying.
Thank you. And she has asked another question: how do despacing or interplanar spacing impact in crystallography?
Very good question. Thank you, Purva, again. Sort of despacing or interplanar spacing. For example, the despacing between planes is sort of related with your Miller indices, right? So D, as you have probably read in your undergraduate crystallography course, DHKL, basically D subscript HKL, it can be used to sort of compute spacing between these HKL values. Now, important thing to note here is that HKL values are limited depending upon the type of crystal system that you're studying. So let's say if you are studying, for example, a sort of cubic crystal class and a simple system. So let's say if you're studying a simple cubic system, there are only certain HKL values which are allowed. So if you go to a kind of a, if you look at this kind of a diffraction pattern for a simple cubic system, you will find that certain spots are missing. That's the very importance of diagnostic tests. Those are known as systematic absences in the Lau diffraction pattern. Similarly, if you go to a kind of a outer diffraction pattern like intensity versus 2 theta, then you'll find that there are only certain 2 theta values at which intensities are present. Those 2 theta values are related with DHKL. DHKL is then related, DHKL or interplanar spacing is then related to the planes which are accessible, and then that relates to the kind of crystal structure that you are studying. In fact, since you asked this question, there's this, the sort of foundation of chemotherapy, inorganic chemotherapy in cancer was these kind of cis-platin complexes that used to bind to DNA, right? So you have platinum and they're like, it's in a sort of, square planar complexes, and those square planar complexes were good enough to sort of hold 2 strands of DNA together, which were like rogue, and they started going apart and replicating and giving rise to cancer cells. So the fact that, these cisplatin drugs bind to, I think they bind to sort of, in a regular pattern on the DNA, they don't bind to the entire backbone. This kind of periodicity in binding was discovered by Jacqueline Barton, who was a student then with Stephen Lippard. You might have heard of Stephen Lippard. They have this very famous book on bioinorganic chemistry. But the presence of these systematic absences and sort of correlation with DHKL values actually helped them understand the method of binding of cisplatin with DNA, which later on went on to become a successful industry. I think platin-based drugs, I'm not sure if they're used now, I'm not a medical expert, but they were at some point of time an important class of drugs for cancer chemotherapy.
Thank you for your answer. And one another question asked by Purva is, do hybridization and coordination number play any role in crystallography?
Yeah, thanks, Purva. Well, I would try to say that coordination number, definitely. So for example, let me see if I have got something like that. Yeah, so this is sulfur and sort of 5 fluorine atoms attached to it. So this is SF6, if you will. And this is a sort of, the coordination number is also sort of inherently in one way related. I don't know if there's a sort of direct kind of relationship, but it is in fact connected with how these things back in space. So example, water is coordination number 2. It is what some people tend to believe is, I think, sp2 hybridized, whereas my apologies, I've really not done hybridization, because hybridization is not a sort of concept which is used much in practice, but it's useful to understand sort of the local atomic structure. And this is, I think, sp3d2, sort of an octahedral kind of hybridization. So hybridization controls the coordination number, as you've pointed out. Coordination number definitely, to a certain extent controls the sort of symmetry of the molecule, and that translates to the symmetry in the crystal. So one that is coordination number 2 will pack in a particular form of way. One that is coordination number 6 will pack in a different way. So yeah, they do play a role, but again, to be honest with you, I am not able to sort of give a very kind of logical relationship as to how they do, but they are sort of related, if not directly, but in an indirect way with each other.
Thank you, Dr. Somakar. Then Omlan has asked one question: what will happen if we use liquid sample instead of powder samples in X-ray diffraction?
Brilliant. Thank you, Omlan. That's a brilliant question. So if you're using liquid samples, so there's this, you might have heard of this thing known as liquid crystals, LCDs, liquid crystal displays, and so on and so forth. So, liquids are a sort of interesting class of things. Like, I mean, there's a huge bit of theory on the structure of liquids. It's very advanced physical chemistry. And I admit I'm nowhere near an expert on this. But when you have gas, it's essentially amorphous. And then you have solids most of the time. I mean, it would not be correct to say gas is amorphous, to be honest, but gas, the molecules are far apart. And when you come to as you move towards a condensed phase, there are molecules coming close together. In solids, they may have well-defined arrangements, which is crystal. Now, liquids can be somewhere sort of in between, depending on the type of liquid that you are studying. And I mean, you would not be able to do, I mean, I know that I have not done this myself, but I know that people put in liquid samples in crystals, like how you mount a single crystal, you know, in a powder diffractometer, you put a tube of liquid. The tube has to be X-ray transparent, of course, and then put it in the kind of regular theta to theta geometry of collection. Now, because liquid has much low level ordering, I would say, like very, very, very local sort of ordering. Like, let's say there's a water molecule and there are two more, and then there's a bit of, you know, fluctuation, and then there's two more like this. So a sort of local ordering as opposed to ice, which is long range ordering, you will get some kind of response. And this kind of responses are usually known as radial distribution functions. Read about them, because this is a very, very, very interesting area that we've asked. And these radial distribution functions actually tell you how the R distances sort of repeat over time. And you can find out information about radial distribution function of liquids from crystallography as well. If it's water, then probably you would be better off doing neutrons. If it's something slightly heavier, then definitely maybe X-rays. And especially if you have sort of local order in liquids, more well defined, like, you know, these, I think they call as nematic phases and sematic phases. I've now forgotten the terminology in liquid crystals, but they are sort of like local strands in a kind of semi-condensed area, semi-condensed structure. At that point, crystallography becomes extremely important. So yeah, liquids can also be studied using X-rays and neutrons in one way similar to crystallography, but with slightly more local level information than long range order.
Thank you very much. And till now, all the questions have been answered. So you can move on for your remaining part. Thank you.
Thank you, Dr. Roy. I'm sorry, I think I've again sort of just touched the clock. My apologies, I've always tend to sort of overshoot the time, but there's hardly one or two more slides. A little bit more, you know, in terms of, you know, I've talked about large scale structures. Now something sort of in between. For example, in case of proteins, you have these kind of polymers, for example. The question that Purva, you raised was basically, you know, they have these kind of local kind of fluctuations. For example, if it's, you know, if it's a protein, for example, proteins are essentially also polymers, right? So these kind of external linkages, they fluctuate. And there are also things such as diffusion. I'd mentioned these things yesterday, and these can be studied using other kinds of techniques. So if you're studying fluctuations, the scattering is elastic. You don't really want it to transfer energy to the system, but it is incoherent. X-ray diffraction is elastic scattering, but it is coherent, right? Coherent means there's a sort of well-defined direction in which the scattering is occurring. If it's incoherent, then you can study the kind of the elastic incoherent scattering with neutrons, and you can find out fluctuations in molecular chains. Another bit of information at the kind of local molecular level. Then, for example, if you're studying diffusion in systems, then what you can do is you can do a kind of a quasi-elastic scattering. Again, as apologies for this kind of like jargon, elastic, quasi-elastic, inelastic. There's sort of very subtle differences with respect to each other. But, you know, the neutron goes and hits your sample, and, you know, there's a slight exchange of energy, which is not fully inelastic, neither fully elastic. So it's called quasi-elastic. And you can do these things and find out diffusion coefficients. So these are other levels of molecular phenomena that you can do. And having spoken a bit about neutrons now, you know, neutrons are a rich source of information like X-rays. But just like X-rays, you would also need high energy sources of neutrons. These can't be generated in the lab, so they need access to neutron beamlines. In our country, we have the Dhruva reactor in BARC Mumbai, which you can go to if you want to do any kind of neutron diffraction experiments. And there are sort of a large number of international neutron beamlines. I've myself been to this wonderful place called the ILL, and this is located in Grenoble in France. You might have heard about Grenoble because that was where an unfortunate incident happened. That was where I think Michael Schumacher had his sort of skiing accident a couple of years back. And this is very located. There are two beautiful rivers, the ICR and the Drac River, and this is the sort of ring in which neutrons are generated. Nice little town in France. And again, access is free. The government pays for it. If you have any plan, if you have a research proposal, you do encourage you to submit it to these kind of centers. Like I had spoken about synchrotrons earlier, they evaluate your proposal, and if they find that the science is worth doing, they sort of sponsor your travel and your experiment there, and you get to do amazing bit of science and world. Right. So small case study with this, and this was basically, I was looking at, this is again a sort of neutron scattering work that I was lucky enough to do at ILL Grenoble. So I was looking at hemoglobin, which is a sort of carbon dependent, a high carbon rich, it's a protein, so it's got all carbons and hydrogens. And I was looking at hemoglobin in solution, and I've done essentially these two kinds of experiments. So this is what is known as a quasi-elastic neutron scattering, and this is supposed to be a delta function if it is purely elastic. It slightly broadens out if it is quasi-elastic, and by studying this kind of line width broadening, now just a sort of important aside here, line width or the broadening of spectral line shapes, broadening of lines, they are a storehouse of information. So if you, in this kind of an experiment, if you study this, you can find out diffusion coefficients. I had managed to find out diffusion coefficients of protein in solution and protein inside silica nanostructures. And in solution also, you have these kind of fluctuations because of the polymeric backbone. And this is the kind of information that you get from elastic neutron scattering, where you plot the sort of root mean square deviation of the backbone as a function of temperature. And you can actually sort of get this kind of variations. I receive this kind of, I observe this kind of variations. And by looking at this, you can comment on, for example, the sort of rigidity of the backbone, and you can define things like rate constants. Apart from this, these were experiments that I had the opportunity of doing. So I just thought about sharing them with you. Apart from this, if you're looking at neutron scattering, you can also study other kinds of phenomena, for example, sort of local kind of phonon vibrations in crystals, local disturbances in crystals, so on and so forth. So a lot more information that can sort of seep in depending on the kind of experiment that you're doing. And this brings us to the overall sort of picture that I've been thinking of building till now. We started with atoms, moved to bonds, moved to molecules, moved to sort of local interaction, and then moved on to crystals. And apologies, I talked about a lot of techniques, some of which you'll be studying as a part of the self-development course, some of which will be just sort of follow-ups, and you can just follow them up in separate projects, or if you're ever interested in doing an internship in a lab or something, these things might come in handy. So at the atom level, you start with NMR, and this goes on to chemical environments around the atoms, extending to bonds, molecules, and local molecular environments. At the bond level, you have IR and Raman spectroscopy. At the molecule level, you have UV visible spectroscopy, X-ray absorption spectroscopy, a bit of circular dichroism, maybe not at the molecule level for CD, slightly higher, a little bit of fluorescence. Fluorescence also effectively also proves this kind of bond making, bond breaking. At this domain, I have not talked about them, but you do also have laser spectroscopy, things such as ultrafast spectroscopy, which are sort of inherently connected with kind of, real life chemistry. Like I spoke about Ahmed Zuel at Caltech yesterday. So he was the pioneer of studying transition state using laser techniques. And so laser techniques also lie in somewhere this region. Now, if you go to slightly molecular based sort of intermolecular kind of interactions, chirality, a sort of very, very, very important property in chemistry. You get to do circular dichroism, local environments in X-ray absorption, a little bit on things like elastic neutron scattering, quasi-elastic scattering, small angles. I've not talked about small angle scatterings actually, to be honest, but this also provides information more connected with, for example, the question on liquids that Orindam you asked, that small angle scattering can prove information on radial distribution functions in this area. And then when you go here towards extended crystals, you have X-rays, neutron diffraction, so on and so forth. So this is the sort of toolkit in one sense that I promised when I had sent in the abstract for my talk. And if you start a research group, if you join a lab, if you're working in a R&D environment in industry, and you're given a random thing and you're being asked to identify techniques which can be used to characterize and understand those materials, then this would probably help you to sort of have a decent start identifying which technique to use depending upon what you want to do. However, there are a few things that are still left for you, obviously. Otherwise, it just ceases to be interesting, right? So these are the kind of tasks that you can do as a sort of follow-up. This is a kind of a length scale based map that I've tried to draw. This is the length, increasing length scale, different kind of techniques that you're using. However, you can also have a time scale map. depending upon, let's say if you're sort of probing dynamic phenomena, then you would want, let's say if you're wanting to probe bond breaking at 10 to the power minus 15 seconds, what is it called? I think it's called femto, right? Femtosecond spectroscopy. What sort of a tool would you use? Now, for example, if you're looking at diffusion of protons in a solid plastic, it's much slower, let's say of the order of milliseconds. What kind of technique would you use? So try to do a transformation from length scale to time scale. We've talked so much about Fourier transforms, right? It's like changing from frequency to time and so on. So think of this as your own transformation. Now, apart from this, you would probably also want to do a little bit of reading on, my apologies, there's a little bit of background noise because of a vehicle passing by. Right. You'd also want to read a little bit about electron diffraction. You've probably already listened to a talk on electron microscopy. Read about electron diffraction. The physics is similar to X-rays and neutrons, but where does it differ? And when would you want to do electron diffraction instead of X-ray diffraction? Something worth thinking about. And the last or important part, this is something that I definitely encourage all of you to read, is cryo-electron microscopy. The reason why I'm saying this is because this has a sort of a huge contribution towards understanding and designing the coronavirus vaccine. And if you go back to crystallography, sorry, quickly taking you back. So you have a single crystal, you sort of rotate it on the diffractometer and expose different facets, and then you get these kind of diffraction patterns, and then you solve for the structure. Now, for example, if you're unable to get a crystal, for example, there's the coronavirus, it might be difficult to crystallize, it might be difficult to work in a lab with the virus, afraid that you might fall ill with the virus yourself. So in that case, a sort of alternate approach would be taking this in sort of liquid and then freezing it, assuming that in liquid things are always fluctuating. And because if you freeze a liquid, you essentially have snapshots of the molecule with different phases exposed. And if you take a sort of combination of these snapshots, you can actually get the entire molecule. So this is sort of a very kind of top level, basic layman's approach to cryo-electron microscopy. And in fact, this was used in order to synthesize the overall crystal structure of the virus. Remember the structure that I'd shown you yesterday in that kind of a timeline? The structure of the coronavirus binding with the ASQ was actually solved by cryo-electron microscopy. So read on about this and you'll be happy. I'm sure you'll find it interesting in the kinds of way that you'll be able to connect data obtained from here and data obtained from crystallography. Right, and this is the sort of take-home exercise for the day. A set of reading, I'll send over the slides to Dr. Roy, and he'll be I'm sure he'll be happy to share them with you. I've also taken the liberty of putting together a sort of 2 or 3 page study guide on these kind of techniques, major techniques, not all of them, and a sort of small set of assignments. I'll again be happy to send them over to Dr. Roy at the end of the day, maybe tomorrow. And so I have reached the end of my presentation. I'd just like to take some time to acknowledge the sort of funding for the experiment. There's a little bit of experiment that I've shown for my work, and also funding from different agencies which has helped me study these techniques as a part of my job. Funding from the ministries in India, funding from the ministries here in the UK, obviously my alma mater, that's the Indian Institute of Science, the University of Strathclyde, Glasgow, where I was a postdoc, NPL, where I currently work, and these amazing places, international synchrotron and neutron centers, where I've had the opportunity to do a couple of experiments. Again, I keep on emphasizing this: when you're doing your research, do please explore these techniques. The government of India has amazing facilities, sort of amazing arrangements with these institutes where you can actually travel without any cost, do experiments, and they are really life-changing experiences. So I need to put on record my sort of acknowledgements for all these organizations and ministries, and all the best in your study. And because you're all crystallographers, may the light always be with you. And I'm happy to take questions, comments, suggestions now.
So thank you. We are at the end of our 2 days program. So first of all, thank you very much to Dr. Somasdar for your nice presentation. And you have covered a lot of areas, starting from absorption, then emission, finally diffraction. More to say that you have given time from your busy schedule, being a Saturday and Sunday, or we can say being weekend, we have spent time with us. So we are very much grateful to you.
No, thank you, Dr.
Thank you.
I'm happy that all of you took some time to organize this. It's been really a pleasure talking to you. And I'd especially like to thank the audience who've taken off your time on a Sunday to listen to this. So thank you also from my side.
I think there is at least one relevant question, Dr. Roy, if you look it up.
Yes.
On polarity and all that.
How is bond polarity is responsible for specific crystal system?
Bond polarity.
That's a tricky question, actually, to be honest. How is bond polarity related to a crystal system? I'll be honest with you, I don't have an offhand answer to this. I mean, I would tend to think that crystal structures are kind of like symmetry-based packing based on molecules, and they're inherently connected with the symmetry of the molecule. And I can't think immediately of kind of polarity or electronic effects on the symmetry.
Now, bond polarity creates secondary bonds and change interplanar distances and things like that.
Yes, that makes sense. Thank you, Professor Shamsar. Exactly. Yeah, that's actually the thing. So, for example, if you have water, and water is a sort of it is a dipole moment, right? So you have what is known as hydrogen bonds. So hydrogen bond is a very, very, very interesting area of chemistry. And because you have hydrogen bonds, that helps the molecules pack in a crystal lattice in a particular way that probably would not have packed in that way in the absence of hydrogen bonds. So yes, bond polarity resulting in kind of sort of coordination or weak kind of interactions in the lattice, and perhaps that manifests itself in the crystal structure. Thank you, Professor Shamsar. That was a very interesting insight. And thank you for this very interesting question.
Yeah, I think we owe a lot of thanks to this particular person for making this session very lively. Purba Bandyopadhyay, from on behalf of the organizers, we particularly thank you very much for taking such keen interest in today's session. Thank you. And just one more announcement, just that if some of you have asked for feedback, please feel free to give the feedbacks in the chat box, okay? Anirban, please proceed. I'm sorry I interrupted.
Yes. Another question is there. What are the different techniques to characterize crystals and chemical crystals? That question is asked by Akshay Kumar Moore.
Okay. So I assume, like, I'm not sure, Akshay, thanks Akshay for your question, first of all, but I'm not sure I understood the sort of distinct sort of difference between crystals and chemical crystals.
Exactly.
The difference they're meaning by metallic crystals and, you know, NaCl and stuff, ceramic and stuff like that, or maybe organic. DNA being a crystal, I mean, but typically that is the chemical crystal class.
Right. Thanks, Akshay. Sorry, I was not able to get it in the first kind of first instance. But yes, I mean, let's say you're studying something like alloys. Those of you who are interested in pursuing a career in metallurgy, let's say, if you're studying alloys, you have like copper, iron alloys, and something alloys. Let's say ideally alloys may not be crystalline. Let's not go into that. But let's say you have metallic systems, right? And the kind of crystal structure, for example, if you're studying copper or something like that, the kind of diffraction that you'd probably want to use is X-ray based diffraction, because copper is a high electron density system. Now, let's say if you have something like superconductors, a sort of very important area, right? Most of you are aware of this. So you have copper, yttrium, that's a fancy kind of high atomic weight element sitting there in a lattice. Definitely go for X-rays. On the other hand, if you're moving towards, like, I agree that DNA and most of these biomolecules were solved using X-rays, but now because neutrons are also sort of available for use. So if you're going more towards, let's say, binding of a drug with, let's say, a protein, sort of high organic based polymer, carbon, hydrogen, oxygen rich systems, go for neutron based diffraction. And if you have such a system where you cannot have a crystal at all, let's say a kind of amorphous alloy or something like a liquid, it's not just crystallizing. The crystals are sort of serendipitous. You can't really just ensure that the crystal is grown every time. In that case, go for things like, if it's a liquid and a molecule like a virus, not a virus, like some sort of an unhealthy sample, but let's say something like a protein or something, go for cryo-electron microscopy, which is, I mean, it's easy to say go for cryo-electron microscopy, but I guess there are a limited number of cryo-electron microscopes all over the world. But yeah, that would be the technique of choice. If it's amorphous samples, liquids, go for small angle based scattering techniques to find out radial distribution functions. And yeah, that's sort of just a sort of broad array of techniques. Thank you. Thanks, Akshay.
Thank you. Thank you. Nicely. So finally, we are at the end. So now I'm requesting our HOD sir conclude this session by giving this concluding. So what do you say?
Okay, thank you, Dr. Roy. Before I get to the concluding part, couple of announcements, in the sense that there have been curiosities expressed. As our speaker mentioned, he is going to share the slides and some other literature, but we would need a bit of time. So what I suggest that you email, the contact email is given in the flyer, or Dr. Anirban Roy is the coordinator. So Dr. Anirban Roy, if you put your email address in the chat box. So those of you who are interested in receiving the slides and other learning materials, please email Dr. Anirban Roy, and you do so on Wednesday. Before that, we won't be able to furnish that. We'd need a little bit of time. So that is the way to get it. And the other part is here, it is not, there is no provision for any certificate. We believe that the learning you got is good enough a certificate. Then some of you asked if the video is going to be available. Would like to see, I hope we have the permission of the speaker. We'll try to see if we can put it up in the YouTube, and that would, we would need 2-3 days on that. So once we get it, those of you who would be sending us emails, so we would send you the links. So that is more or less, Anirban, am I missing anything as far as
No,
announcement related stuff?
No,
most of the things have been covered. Okay.
Yes.
Okay, so this is a moment we say goodbye to this session and the speaker. We must thank the speaker. We must thank the audience, and some of the members of the audience have asked really probing questions, and that's I'm sure that has stimulated the speaker. Now, what Dr. Rudro Samajdar did, in my opinion, he painted a huge canvas, a very large canvas. He painted it with broad brush strokes, yes, but he gave us an overview. That was what he and I, when we had a conversation, I requested him if he could give us an overview. What happens is most of the time we miss the forest for the trees. We know too much of detail of too few area. There is something called who is a specialist, who knows more and more about less and less, until the person ends up knowing everything about nothing. So I did not want him to make us a specialist here. I requested him if he could paint a big picture, which would give us an idea what to choose when. If the length scale is like this, what kind of options do you have? If the chemistry, for example, if the material is like that, what kind of, if what is to be probed is made of this sort of like heavy, a high electron density, what sort of probing ray do you use? Also in different, for example, this time scale which he had indicated, that if you are trying to measure or trying to inquire into the very fast breaking and making bonds, what is your instrument or light of choice? So choosing the right kind of light, we have got a rather good overview. And for that, I thank you very much on behalf of the Department of Material Science, Technology, Science and Technology at the University of Maulana Abul Kalam Azad University of Technology. It's a rather, the department is in its childhood, or rather, I think it's childhood. We haven't been, we are not even adolescent yet. So on behalf of that, we thank you, Dr. Rudra Shamasdar, and we would like to express our appreciation by offering you a certificate of appreciation if Dr. Roy show one.
Thank you very much. Thank you.
Is it visible?
It is. Thank you.
So we would be emailing it this to you shortly.
Definitely. Thank you so much.
And again, now on behalf of the university, on behalf of its Honorable Vice Chancellor, who actually yesterday put a very, how should I put, an apt phrase to capture the spirit of this seminar, that it is to evoke curiosities, hidden curiosities, and latent curiosities. And I think our speaker has done that in this two-day session. We thank him. We thank the organizers. For example, Dr. Anirban Roy has done meticulously preparing everything in time. We appreciate that. We thank Mona Lisichar being in the background. She could not be here yesterday, but she's the person who looks after the development of our lab. She's very busy with that. And we thank most, perhaps saving the best for last, the audience who have been quite participative and at times extraordinarily stimulating. So with these words, we thank you and we say goodbye, but not without extending a standing invitation that if and when you visit Kolkata, please do take a little bit of time to see our campus in Horinkata. Thank you.
Definitely would be happy to. Thank you.
All right then.
Thank you.
Okay.
And have a great Sunday. Namaskar.
Thank you. So we are logging out. Thank you to the participants also. So thank you, Dr. Shamasdar.
Thank you so much, Dr. Roy. It was a wonderful time. Thank you to the audience and have a great Sunday ahead. Thank you for your time.
Exactly, same to you.
Bye.
Goodbye to all of you.